Hello and welcome back to another video with It's Dr. Dan. And today we're going to be further looking at how to prepare for your Chem 3A ACS final. So in this particular video, I'm going to go through the exact topics that you need to review for your exam. So we're going to go chapter by chapter, and I'm going to talk about which concepts you need to know how to calculate and which concepts you need to know the theory behind in order to succeed on your test. If you study each of these concepts, you will most likely be able to score anywhere from an A to a B, but only if you do spend the time to go through them and to review them very, very well. So I would recommend that being this is your final exam, if you are counting on this test, you need to spend the time to study every single chapter, at least to an extent. Usually, when it comes to reviewing for this type of exam, you probably will have to study anywhere from 4 to 8 hours of your time to really be able to review it. You could go through all my review videos on it, which would be a start, but the big thing is making sure you go through all the different problems to master this. Now, if you haven't seen what the format of this test is, please go to part one. And if you want to know what these types of problems look like, refer to part three or maybe part four or beyond, depending on how many I decide to make, which will go through example problems and how we can actually break down and to succeed at these types of tests. Okay, let's take a look. The first chapter was all about measurements and dimensional analysis. In my course, we focused for the first couple weeks of the class really just focusing on, can you do calculations? Do you know your math basics? And now when you're going through this, the way I'm going to kind of situate all these different chapters is telling you what you need to calculate and what theory you need to know in terms of how to answer a theoretical question. So when it comes to the calculations, most of these just come down to, can you convert units and can you do just simple word problems on how to convert from one thing or to another? So, for example, one of the first things that you did a lot of conversions with was the concept of density. So, you will have to do density driven calculations. So, make sure you remember that, hey, that's grams over milliliter or kilograms over liter or kilograms over milliliter, knowing that's always a mass over a volume when you're doing those different amounts. The other thing that you will have to know is how to take approximations based on info given, right? There might be multiple problems in a row that might all have to do with each other, and they might be about similar concepts. So, can you do approximations based on that? Now, after that, there's also sig figs, right? So, do you remember your basic sig figs rules? All semester long, you've had this drilled in your brain between whether it's your homework, your quizzes, your exams, your lab reports. Between my open math and doing the different assignments, you've had to do sig figs. So you should know them better than anything else. Better hope for 60 sig fig questions because you'll hopefully get them all correct. There's also temperature. So you need to know how to go from Kelvin to Celsius, right? So all the different SI units when you're going through that. Now, the other concept that you need to know as well is when it comes to the theory is about the scientific method. So do you know the difference between what a law is, a hypothesis, experiment, theory? And if you're like, oh, I don't remember any of those, go back and review them. They're in your notes from probably the first week of the class. Review them, see what they are, just so you remember. Atoms. So when it comes to discovery, it was more like, how are the protons founded, neutrons, electrons? Knowing those little basic techniques of how we came to know that we had positive particles, negative particles, and neutral. So knowing those basic ideas. Now, when it comes to calculations, this all had to just do with counting. So can you count how many protons, neutrons, electrons there were? And a lot of this came from your periodic table, right? So if you have, let's say, the atom, let's say helium, for example, and above it, it had the number two, and then below it, it had the number 4.008 underneath of it. Do you know what all those different pieces represent, right? So when we're looking at them, we know, hey, this is your atomic mass. We have our atomic number above it. And then we know, all right, the atomic number represents the number of protons, whereas the atomic mass is protons plus neutrons. So you can kind of do some simple little um, calculations to figure out which one is each. And we'll go through this a lot in different videos as well. and then how to calculate your charges, right? Remember, atoms are inherently neutral, and ions, when it came to cations and anions, had more or less electrons, which a lot of that was covered in chapter 3. So let's look at that. But when it came to essentially chapter 3, this was all about all the different atoms, which groups are they in, and what it came to how we can count electrons. So the first thing really is, well, do you know how the periodic table is organized? Which mainly had to tell you that, okay, they were in groups. They were known as alkali metals, alkaline metals, halogens, transition metals, noble gases, just to name some of them, right? So you had the metal section, the non-metal section, and that is like your theory part. Can you name the groups? Can you situate where they're at? When it came to calculations, could you count how many valence electrons there are, right? Earlier, I showed you a periodic table and I showed you a trick on how to count valence electrons. I showed you that in previous videos as well. Can you count just the regular amount of electrons when it comes to a neutral or a cation or an anion, right? If you see a positive charge, that means less electrons. If you see a negative charge, that means more electrons. Can you count them? Can you also do electron configuration? And that might be, 1s2, 2s2, 2p6, so forth, which you're like, oh my God, I haven't thought of that in forever. Well, these are things that you need to review and try to make sure you understand so that way you're not getting caught with it. Generally in this test, luckily there's no real like quantum mechanics calculations. So it's very rare that you'll ever see like an energy calculation or a light calculation. It's all about, can you organize your electrons and be able to understand how the atom essentially is labeled. Let's look at chapter 4. Chapter 4 is all about compounds and bonding. So now that we have our electrons that are going to either be shared or taken, right, you have to know when it's covalent or when it's ionic. Covalent is when you have nonmetals together that are sharing electrons. Ionic is when you generally have a cation and an anion, and then the cation is mainly a metal or ammonium, right? Those are the only two. So if you have a cation, it will give its electron to the anion. You need to be able to swap, drop, and balance charges. So if you don't remember what I'm talking about there, so if you think like, okay, I have barium 2 plus, I can get that from the periodic table, and C minus. I could swap, drop their charges and be able to see that, oh, I have BaCl2 as my molecule, right? Barium chloride. Now, the other thing is, as well as you need to be able to name them too. So I'd recommend remembering your naming principles. Also, when you're going through things like, let's say if I have iron 3 chloride as a name, knowing that the Roman numerals represent charges. Okay, so if I have Fe, that would be Fe for iron, and then that means it's a 3 plus charge when I am looking at this, right? So it would be Fe, we'd swap drop it and then make it FeCl3 when we're looking at all how to figure out all those different things. The Roman numeral is a charge, not a subscript. Okay, so please, please, please remember that when you are doing this exam. Now, for chapter 5, this was moles and then chemical formulas again. So the big thing is this is mainly calculations. Like, can you calculate molar mass? By adding up all the different molar masses from your periodic table, and then be able to use the subscripts to calculate that. And then when it comes to your calculations, can you figure out how many moles there are within a formula, right? So, for example, if I had, let's say I had calcium phosphate, right? And I were to look at this molecule and I asked you, well, how many moles of each thing do I have here? Well, I could tell you from the subscripts, and this is something that you could count, is that I have 3 moles of calcium, 2 plus. I have 2 moles of phosphorus that's here. And then I have 8 moles of oxygen. And that's by multiplying out those different pieces. So that way you know how to do the different conversions. Now, when you put all these in, they are all equivalent to 1 mole of calcium 3 phosphate, right? Which is our molecule here. So there are many different relationships that you can get from moles and from counting. Now, from there, we had chapter 6, which was all on the molecular shape, electronegativity, polarity, intermolecular forces. These were all very, very conceptual concepts, mainly revolving around theory. Now, what do you need to know? So, being that this was a little bit more of an involved chapter, it had a huge part. We did an entire lab on this. The one thing that you really need to make sure you're comfortable with is how to predict the number of bonds that an element forms, right? Halogens were always one bond. So, a little trend to remember for yourself. So, if you remember your periodic table, right, we have fluorine, oxygen, nitrogen, carbon on the periodic table. When it comes to the number of bonds, right, fluorine always does one, oxygen does two, nitrogen does three, carbon does four individual bonds. Knowing that trend can be very, very beneficial. Knowing how to write your different Lewis structures, right? Can you, based on the knowing the number of bonds, can you draw a simple Lewis structure? And keep in mind, this is multiple choice, right? So the thing is, if you know your bonding trend, you probably will get the correct answer. Um, can you count a resonance structure? Which what that means is, let's say if I had a one of the following molecules, let's say I had carbonate, for example, just kind of coming up one on top of my head, and we were to fill in all of the lone pairs that are here. Well, resonance structure tells you how many other possibilities that you can have for this molecule. Well, the thing is, well, we have the double bond here on the top molecule. Could it move to maybe one of the left or the right structure as a possibility? And the answer is yeah, sure. So why don't I switch it to the side here? And what we'll do is we'll fill in. So we put our oxygen in, our carbon, our single bonded carbon, and we'll move the single bond and the double bond. So here we have another option. Now, is that everything? Well, what's preventing me from doing the same thing where, let's say I put the double bond on the right hand side this time and I put it on the other part? So, how many resonance structures do I have this time? Well, I have a total of three possible resonance structures. So, that's usually all you have to do is count how many different possible structures can the double bond switch to. So, we can see we have three. When it comes to polar and non-polar, this mainly has to do with, can you see, are if you have the same atom, they cancel out, and does it follow, what geometry does it follow? If it's the basic geometry and the same atoms all around the central, then it's going to be considered non-polar. Just for the purposes of this test, in order to see if it's polar, is if there are lone pair electrons around the central atom, then it is polar. Okay, just to make it easier for yourself. So, for example, something like that is, let's say I have ammonium, which has a lone pair on it. This is something that would be polar because we have those lone electrons on the nitrogen versus all the hydrogens that are surrounding on all sides. Now, we also need to know our intermolecular forces. So, does it have hydrogen bonding, dipole dipole, dispersion? Can you remember those different forces? Chapter 7. Chapter 7 was all about mainly knowing your calculations. So, when it comes to heat, so your MCAT equation, that's the only thing that you'll have to calculate. So, can you solve for any of the different variables, whether it's Q for heat, M for mass, or the change in temperature, which is delta T. Remember, this is one of the formulas that you need to know off the top of your head. So remember the MCAT equation. And then keep in mind that specific heat can be in both joules per grams per Celsius or in calories per gram per Celsius. Realize though that Celsius too. So look at the units that are given to you. It gives you a lot of hints that are in the problem. In terms of theory, you have to know like what like properties does a solid, liquid, and a gas have, and that has to refer to like what's its shape and its volume. Is it definite or is it indefinite? So like a solid has a definite volume, a definite shape. Volume generally has a definite volume, indefinite shape because it can take the shape of any container. From there, knowing how phase changes are referred to as physical changes, meaning that when that happens, you do not break it down into anything else. So if you were to freeze water, it hardens and turns into ice, but it's still water, right? It's just a water in solid form. If you boil water, it's going to start bubbling, And those bubbles, right, are water, right? Steam starts coming off. This is a physical change. Um, when it comes to exothermic or endothermic, realizing how heat is transferred. So, is it something that's absorbed from a system? Does it come off from it? If it feels colder, it's absorbing it. If it's something that feels hotter, it's releasing it. So, let's take a look at our next part. So, in chapter 8, what we learned about was gases. So, when it comes to gases, it's mainly calculation focused. Now, the good thing is that you really only need to know two gas laws when it comes to solving anything when it comes to gases, and it has to do with either the ideal gas law or the combined gas law. So the first thing is, well, when do you know to use both? This was an entire thing that I covered in many other videos, so I'd recommend reviewing the gas laws if you need help. And it has to do with whether or not there's no change or if there is change. Now, how can you tell? Well, if there is change in the system, then it has multiple pressures listed, multiple volumes, multiple temperatures, multiple moles. No change lists one variable for each thing. So like one pressure, one volume, one moles when you're going through the calculation. So if there is change, you got to use the combined gas law. If there isn't, then you want to use the ideal gas law. It fully depends on which type of problem you have. And then when it comes to the combined gas law, if you have anything that's constant, you can remove that variable. So, for example, if I had temperature and moles, they were constant. So what you can actually do is we can erase essentially everything that's on the bottom, and then you'll notice that hey, we now have Boyle's law because temperature and moles were held constant. Whenever something is constant, it can go away. So keep that in mind when you're looking at these problems. In terms of theory, it's mainly the conceptual thing. So, like, do you know how the gases will behave if another one is changing? So we did these examples a lot in class. So for example, if volume is increasing, pressure is decreasing. So a lot of this you can actually get from the formula from the ideal gas law. So if you know how to kind of do to use this thing, you can do a lot of simple little tricks. So one thing is, let's say if I wanted to see how does volume and pressure change. Well, let's say, for example, if the pressure is doubled, what happens to the volume? So what you can actually do is we can make some little assumptions here and plug in some like fake numbers. So let's say if the volume is doubled, so I have one atmosphere on one side, two atmospheres on the other, and I want to know what happens to a volume. So why don't we make it really easy and we'll say we have 1 liter. So what's the new volume? So, what can we do is we can essentially just rearrange our problem. And what you'll see is that, well, when I move two atmospheres to the left, you have one divided by two, which means it's equal to 1/2. So, your new volume is 1/2 of your original volume, which was 1 liter. So, when you double pressure, you're going to be having your volume. So, as pressure increases, volume decreases. There are little trends that you can try to solve when you're going through these, when you're trying to do the math to see, like, all right, well, I don't know what's going to happen. I don't know how to guess it. Just come up with a simple number to be able to explain the concept, plug it into the formula. It's a trick that I've been using for a very long time in order to understand math. Now, when it comes to chapter 9, this also has to do with solutions. So solutions, there was a lot of things that we did. We did multiple labs on how to do net ionic equations, how to do solubility, how to do molarity, and we drilled a lot of these different things into your brain. So the big thing is well, when it comes to calculating molarity, make sure you're comfortable with getting something into moles and then dividing into liters, right? If it starts as a mass, can you convert to moles? Can you divide it by the volume? Knowing when to use the dilution formula, right? You got to look for that keyword dilute. If you see that, that means that that is the formula that you have to use, but it's up to you to be able to recognize it. Now, when it comes to concentration solutions, the biggest ones actually have to do with the following, which is mass over volume versus weight over volume, right? So if you see an M, that refers to mass. W means weight, which, like, wait, what's the difference between them? There frankly is not a difference between the two. They are used interchangeably in the health field, which is one of the reasons why it's so focused on in this test, because many of you want to become healthcare workers. So this test is geared at you. So when it comes to these, is realizing that it's always referring to grams of your solute all over 100 milliliters of your solution when we are dealing with weight over volume. So keep that in mind. You'll also have to do concentration of ions. So if you're starting with, let's say, like this example up here, and I have 1 molar of copper hydroxide. What does that mean? Is that if I do a conversion here, and let's say this is aqueous, just so we have get rid of our argument here, we will have a 1-to-1 ratio based on the coefficients. So you're going to have one, you could convert that to be 1 mole of copper, 2 moles of hydroxide based on the coefficients, right? When you do the mole to mole conversion. So those are like kind of the little things to keep in mind when you're doing these. Now, when it comes to theory, there's quite a bit that actually gets applied. This is probably one of the bigger chapters that gets tested on the most. So this one might be a really good one to focus on. The first one is, do you remember colligative properties, right? So there's boiling point elevation, osmotic pressure, and then freezing point depression and boiling point elevation and osmosis were the three colligative properties. So knowing that with osmosis that you'll have a water will flow into an area of high concentration is one really big one. And then knowing like hypotonic, isotonic, and hypertonic solutions. Mainly when it comes, I use an example in my videos around red blood cells. I would recommend going back to the colligative property video and reviewing that concept. Being that class does translate into physiology and anatomy, these concepts tend to be tested on at least once in a lot of these exams. Now, when it comes to solubility, the big thing about this is you're not given your solubility table, but you're never asked any type of really weird solubility trends. The biggest thing to know is if you always remember what is soluble, you'll be fine. Which always was the abbreviation of ANA when it comes to what is always soluble. So it was always ammonium, acetate, nitrate, and then the alkali metals are what is always soluble. So keep that in mind when you are reviewing these. Let's look at our next chapter. Chapter 10 was all about how chemical reactions work. So the first thing is how to balance a chemical reaction. You need to know how to do that, right? That is step one when it comes to the chemistry course. If you don't know how to do that, then there's a good chance you might not get the grade you want in the end, right? You need to know how to balance. The other thing is, can you identify the major types of reaction, right? There's combination, decomposition, combustion, double replacement, single replacement. There's 5 major types. And that was something that we talked about in a previous video, types of chemical reactions. Can you identify? When it comes to oxidation reduction, really the only thing you're looking for is, does the thing lose electrons as an oxidation, or does it gain electrons as an reduction, right? Leo goes Gurk. Can you identify loss and gain of electrons? When it comes to the net ionic equations, the big thing is solids and gases are what is kept in the net ionic equation. And the other thing is you know what ions make it. So like for example, if we go up to this problem here and we wanted to kind of look at, well, how would I show the net ionic equation? Well, this here is a net ionic equation because it's showing that copper hydroxide broke down into copper 2 plus copper hydroxide. We kept the solid and then we kept the ions that actually broke it up, right? If you switch that, you would get your standard net ionic equation. Luckily, there's not many of those, but you still need to be able to recognize them. So look for those solids. Now, stoichiometry, this one is a big calculation topic. Big thing is broke it down into what you need to know. Luckily, it's not a ton. The first thing is, can you do like a mole to mole conversion? So can you read a balanced chemical equation and convert? Can you do something like maybe milligrams or kilograms, 2 grams to moles? So using your prefixes. Can you do mass to mole to mole to mass, right? So using your chemical formula again to do that. So that would be like the step here in the middle. Can you do that mole to mole ratio, which is crucial? And then can you do a limiting reactant problem? Now keep in mind, this is where like the tactfulness of you taking your test is key. If you come across a limiting reagent problem, meaning you're given the amounts of two different species, this might be one you want to come back to because it's something that's going to take you potentially a few minutes to complete. Remember, they're all worth the same amount of points. So this could be one you could go to later when it comes to those points, when you're going through all of them. Let's look at chapter 12. Chapter 12 is all about acids and bases. So when it comes to calculating, the one thing you need to be able to do is calculate pH, which I should have put this formula above, but pH is equal to the negative log of H plus. So this is the one other formula that you need to know that I forgot to put above. So, okay, there's one more. So you need to do that one. You need to be able to identify a conjugate acid base pair, right? So remember, they differ by one proton. You need to be able to identify your strong acids and bases. So remember, acids always have H plus at the beginning of the name. So that is always an acid. And then a base always has a cation followed by hydroxide at the end of the name. So it has to be something that's like usually a metal that's in front or something with a positive charge when you're trying to identify that other species. You'll have to be able to interpret the Kas of acids and bases. Remember, what does that mean? Is that the higher the Ka is, the more it's over one, the stronger the acid. The lower that value is, the weaker the acid. And when it comes to these, right, strong acids, they completely dissociate into all ions. So this is K is greater than one. And when you have a weak acid, that means that you'll still have some molecules left over and K1 will still be existing. So like here we have HA, you see that they're still in solution versus this other species, you see that they're all broken down into their individual ions. So knowing the difference between the two is really crucial to succeeding on questions on this test. Can you identify the differences? Let's look at our last two chapters. When it comes to equilibrium and then the final chapter, which is nuclear chemistry, biggest thing when it comes to equilibrium is can you interpret Le Chatelier's principle? Meaning, like, do you know how a reaction is going to behave when you apply a stress to it? So, do you know like some keywords like pushing a reaction to completion, which means how do you push the reaction forward? Or how do you mainly keep it as reactants, which will push the reaction backwards, right? Can you figure out what direction it's going? Do you know how to increase a concentration, decrease a concentration? That's the only thing that you really need to do with the theory. There's not a ton when it comes to these. So if you can know what those four concepts do, which were concentration, temperature, volume, and catalyst can do, you will be completely fine. So it's temperature, volume, pressure, and then how does a catalyst behave, right? So those are your four concepts of what to look for when we're trying to answer this type of test. Now, when it comes to nuclear chem, which is our last chapter, alls we're going to be doing here is we need to just mainly balance nuclear decay, which is the main thing. So knowing how to balance like alpha, beta, positron, gamma rays, can you balance those equations, right? You have to conserve mass. So the atomic mass needs to be the same on both sides. The atomic number needs to be the same on both sides. So can you do that for nuclear decay and bombardment equations? And then can you solve a half-life equation? So could you do each of those things? So those are all going to be calculation based. There's no theory with this one. It's all calculation. So being that this is also one of the most recent things in the class, hopefully this is one of the things that you'll get really easily as well. Um, so This has been every single topic that is covered in our final. I would recommend fully going over them so that way you're familiar with them. I know this probably wasn't the most exciting video, but I wanted to give you that complete rundown, the complete list of what to study when you're going through your notes and how to break them down by chapter. So I hope that this helped you be able to do that. Please come back for my next few videos, which will be going through the different problem sets and exactly what the thought process is of how to go through them, which will review a lot of the types of problems that you're seeing here as well. All right. Thank you so much for coming by. I hope that this video helped, and I'll hope to see you all in the future. All right. Bye now.